Performance planning. One of the overriding factors in aircraft performance is the density of the air, which decreases with a gain in altitude. Lift production by the rotor system relies heavily on the available air density and is adversely affected as the aircraft ascends. Since rotor thrust is dependent on lift, helicopter performance ultimately decreases with an increase in altitude. For a given total rotor thrust production, a decrease in air density requires a compensating increase in the angle of attack on the rotor blades, which reduces the lift-drag ratio. The ratio of total rotor thrust to rotor drag is upset because of the increased angles of attack, with the result that total rotor thrust production incurs increased rotor drag. More power is then required to overcome this in order to maintain a given performance. Performance is defined as airframe, power required to hover charts, engine, power available charts. Definitions. Pressure altitude. The height above the standard datum plane, which is a theoretical level, which the weight of the atmosphere is 29.92 hg. It is the indicated height value on the altimeter when it is adjusted to 29.92. A high barometric pressure produces a low pressure altitude and performance is improved. A low barometric pressure produces a high pressure altitude and performance is decreased. Density altitude. It is pressure altitude corrected for non-standard temperature. As the density of the air increases, aircraft performance increases, and conversely, as the density of the air decreases, aircraft performance decreases. As density altitude increases, engine power produced decreases, rotor blades are less effective, and overall performance is decreased. Since we do not have a gauge in the cockpit to determine density altitude, we must have another way to determine this. One method is to use figure 4-1 density altitude chart in the RFM. Another method is to use a rule of thumb as follows. To estimate density altitude, start with the pressure altitude and add 120 feet for every degree Celsius above international standard atmosphere, or subtract 120 feet for every degree below international standard atmosphere. Humidity also affects density altitude, but not significant enough to worry about in this rule of thumb. Example, 3,000 feet PA and plus 20 degrees Celsius. The ISA temperature is 9 degrees Celsius at 3,000 feet. The difference between 20 degrees and 9 degrees is 11. 11 times 120 feet equals 1,320 feet difference. Add 1,320 feet to your 3,000 PA, and that gives you a density altitude of 4,320 feet. Prior to beginning any aircraft operation, the pilots must complete a planning process to ensure that aircraft weight limitations will not be exceeded during any portion of the flight. The weight limitations, which must be determined and adhered to, are called Mode 1, 2, and 3, maximum takeoff gross weight limitations, which are found in the limitation section of the RFM. Mode 1 represents operations without external load, where the maximum gross weight must not exceed the values set out to in Figure 1-1 of the flight manual. Weights are based on ability to hover on one engine out of ground effect using 30-minute single engine power. Mode 1 operations require a minimum takeoff and landing area of 108 by 133 feet. Mode 2 represents the maximum weight for operations with a non-jettisonable load using normal takeoff and landing procedures without height velocity limitation at a weight not to exceed the values found in Figure 1-2. Weights are based on ability to hover on one engine at a 10-foot wheel height using 30-minute single power. Mode 2 operations require a minimum takeoff and landing area of 108 by 500 feet. Mode 3 represents operations with a jettisonable Class B external load. Weights are based on the ability to hover using takeoff power. The maximum weight must not exceed the values found in Figure 1-3, and the external load must be jettisonable to one of the following minimum weights. Mode 1, when operating from takeoff and landing area of no less than 108 by 133 feet, and Mode 2, when operating from takeoff and landing area of not less than 108 by 500 feet. Application. The following procedures will enable the pilot to determine load limits prior to conducting any missions. For any planned operations, you must have two pieces of information to complete the performance planning process. the approximate pressure altitude for the operations area, the approximate outside air temperature for the operations area. Information already available to you, but equally important, is the empty weight of the helicopter. This information is found on the chart C in the RFM. The empty weight of the aircraft becomes the operating weight when the weight of fuel and crew are added. The difference between the empty weight plus crew and Mode 1 weight establishes the weight of usable fuel that can be on board for lift operation. That difference between operating weight and Mode 3 weight establishes the maximum weight of the load to be lifted. To determine power required to hover at a known gross weight in known conditions, determine density altitude from Figure 4-1 density altitude chart. Locate the temperature on the bottom of the chart for the known conditions. Establish a vertical line from the temperature until it intersects a diagonal line for the known pressure altitude. Read horizontally in either direction to intercept the density altitude value. Enter for Figure 4-6, power required to hover at 50 feet wheel clearance in section 4, or Figure 4-4, power required to hover OGE in the 10,000 to 14,000 feet density altitude supplement. Horizontally at density altitude determined in step A, and move horizontally until the known gross weight is intersected. At the intersection of the density altitude line and the gross weight line, drop vertically to the shaft horsepower scale. Use Figure 4-21, minimum horsepower versus indicated torque 2 engines, to convert shaft horsepower to engine indicated torque. Establish a horizontal line at the horsepower value. When the horizontal line intersects the diagonal line, read down vertically to the indicated torque percentage. Check Figure 4-20, power available, to verify sufficient power available for conditions. Establish a vertical line at temperature value. When the vertical line intersects the known pressure altitude line, read horizontally to the left for shaft horsepower value. Shaft horsepower value must be doubled for dual engine since Figure 4-20 is based on single engine performance. Compare this number with the shaft horsepower number that was obtained from Figure 4-4 or 4-6 from above. Example: to determine indicated torque dual engine to hover OGE at 65,000 feet pressure altitude and 16 degrees Celsius at a gross weight of 36,500 pounds. Determine density altitude from Figure 4-1. Using Figure 4-4, 10,000 to 14,000 feet supplement, move horizontally at 8,100 DA feet to the 36,500 pound line. Drop vertically to the shaft horsepower line at 6,350. Using Figure 4-21, find 66 torque indicated. Using 4-20, find 3,520 horsepower per engine is available. 7,040 dual. To determine maximum gross weight to hover OGE in known conditions, use Figure 4-5, hover performance OGE 100% NR. Establish a vertical line at the known pressure altitude until it intersects the known temperature. From this intersection, read horizontally to the left to the gross weight value. This gross weight value is the maximum you can weigh and hover OGE. Example: to determine maximum gross weight, you can hover OGE dual engine at 5,000 feet PA and 26 degrees Celsius. Use Figure 4-5, establish the line at 5,000 feet, and read vertically until it intersects with 26 degrees Celsius. From this intersection, read horizontally to the left to the gross weight value of 38,950 pounds. To determine maximum power available under known conditions, utilize 4-20 to calculate maximum power available. Establish a vertical line at a temperature value. When the vertical line intersects the known pressure altitude line, read horizontally to the left for shaft horsepower value. The shaft horsepower must be doubled for dual engine since 4-20 is based on single engine performance. Use Figure 4-21 to convert shaft horsepower to indicated horsepower. Establish a horizontal line at the horsepower value as established in step 3 above. When the horizontal line intersects the diagonal line, read down vertically to the indicated torque When operating at an altitude between 10,000 and 14,000 feet density altitude, you're required to use the supplement located in the back of the rotorcraft flight manual titled Operations from 10,000 to 14,000 feet density altitude. The supplement covers operating limits and performance data. Weight limitations. The maximum takeoff, landing, and inter-route weight for rotorcraft load combination is 35,200 pounds at 10,000 feet density altitude and 28,600 pounds at 14,000 feet density altitude. Linear interpolation is permitted between 28,600 pounds and 35,200 pounds. Center of gravity limits. The CG limits of the rotorcraft external load combination and for the basic rotorcraft are shown in Figure 1-3. They are station plus 337 to plus 345 for all weights between 28,600 pounds and 35,200 pounds. Load should be evenly distributed about the lateral axis of the helicopter. Type of operation. Mode 1 single-engine hover has been demonstrated at 22,670 pounds at 14,000 feet density altitude. See Figure 1-1. Note: linear interpolation for Mode 1 operations is permitted between 22,670 pounds at 14,000 feet HD and 23,900 pounds at 10,000 feet HD. Mode 3 weights are depicted in Figure 1-2. Mode 3 operations are limited to pressure altitude temperature combinations of less than 14,000 feet density altitude. Airspeed limitations. Never exceed speed VNE is 70 kIAS for all density altitudes from 10,000 to 14,000 feet. Configuration limitations. Operations above 10,000 feet is prohibited with EAPS installed. EAPS. These procedures are used if operating above 10,000 feet density altitude.